to understand. This topic is more related with the uh, not the forging deformation process, but this will you will see in the later stages that you will see. You have heard about casting process. This is going to help you ho- uh, how much time required to solidify castings. For example, if you are pouring in this basin, and this is a riser, this is a blind riser, and this is the open riser, and the material comes here, and this is our part. This part is and this is our die upper sand mold, lower sand mold. So I'm just eluding it. It's not required. It's a cavity. We have to pour molten metal into the cavity, and which is the replica of the original part. Replica means it's a negative shape where we have to develop intricate, very intricate, difficult to manufacture by machinery, those parts, and easy to manufacture using the molten metal. But the important part is you have to melt the material in order to pour it. For melting, you need a high amount of energy, furnaces or electrical or burning process. But anyways, so in this case you will understand how conduction happens, how convection happens, how the internal, you see, internally the material starts conducting, and internal temperature reduces. Once it is very very hot, it starts reducing the temperature internally, and the material and this external temperature. So there is a word bo number, where h is the convection heat transfer coefficient, and length is the characteristic length. We will talk more about. So if it is less than 1, then it tells me that it is the internal conduction is very very fast. If it is less than, usually in our cases, bo number is usually less than 1. It means that internally the material, the metal, conducts very very fast, that it remains almost uniform throughout the internal structure. But externally, if this is greater than 1, then a surface temperature is a little bit higher than the internal, so we will not be dealing those cases. But anyways, I'm not going to that. So but the bo number is a good check. We have to apply some check marks. So now my main concern is, so write down a solidification time. How to find out the time to solidify a casting. Okay, there are certain formulae, but let me show you the formula first. Okay, so over here, time to solidify a metal part: volume, density, conduction, heat area, convection, Ln, atmospheric temperature or surrounding minus the first temperature, atmospheric temperature or surrounding temperature minus the second temperature. So this is the time to solidify, time required to solidify a metal casting or a casting. Okay, so there is a little bit theory behind it. So but we will talk about it. Let me solve one question. I'm jumping ahead. I've just given you a formula which is sufficient to understand. Let me show you. Let's go slowly first. I might have missed some slides, so let me show you the slide. Then I'll come back to the. So there are three modes of heat transfer. One is conduction mode, like with a touch, you conduct the heat from one molecule to the other molecule by the touch, or at a solid in solids. We call this conduction. Heat transfer in solids in conduction. Convection is heat transfer in liquids and gases, or we call a fluid, and heat transfer coefficient is H. And radiation is E E stands for emission emitted black body radiation, sigma times T to the power. T is in Kelvin to the power 4. So these are the formula for the um, so now if there is a suppose if this is a plate and this is a thickness 2L. 2L, it could be 1L, but 2L is for our convenience. Because you will see, we usually take the middle of the line, the wall thickness, and then it becomes 1L. So the theory behind it, the D temperature over D time partial derivative equals to alpha second partial derivative of the temperature or second partial derivative of the space, where x, you might be asking, Professor, what is that? So this is my reference. X is from middle of the plate thickness. This is my y value, where alpha is thermal diffusivity. And there is a formula to find out thermal diffusivity. This diffusivity, K is the conductivity, and rho is the density, and C is the heat, specific heat constant. And the time constant, there is a word time constant. T equals to time constant. And the good approximation is the time constant is proportional to the characteristic length square divided by the alpha, where characteristic length is, it is defined as the volume divided by area. This is characteristic length equals to volume divided by area, big V over area. Or we call it as if there's a plate, okay? If there's a plate, very, very large plate, okay? Very, very large plate, and the characteristic length is the half of the thickness of the plate, okay? This is my 2L. That's why we take it 2L. The total thickness is 2L, but half of the thickness is the characteristic length, which is the volume divided by the area. So these are just and if you want to solidify this plate, so external surrounding temperature is represented by T infinity, like our air temperature. Your surrounding temperature, T infinity. Initial, when you are pouring the material inside the plate, is the initial temperature, and when you eject the material, it is the final temperature. Time to eject the material uh, at that temperature. So how would you find it out? So then you have to do some first law of thermodynamics, which is equal to the convection. So over here, this is the surface temperature radiating outside the environment, but inside is conduction. Okay, inside is conduction. A surface temperature is convection. So you have to equate, because heat has to be released to the environment in the end. Okay, so you have to equate both convection and conduction. So heat is released, final minus initial, and that can be written as suppose if we take small change in the heat, convection, and then you can equate it to, which is through the surface, okay, surface, and you can equate it to conduction. Oh, this is taking some delay in my computer, but in conduction, like internally it is conducting, you understand my point? Externally it is convection through the surface. So Biot number is going to, so let me show you. A convection says area times the convection heat transfer, overall heat transfer coefficient times the surface area times the change in temperature for a small time, dq. And similarly, the mass mc delta t. You know that formula for conduction, mc delta t? Yeah, you know that very well. So you have to equate these two equations, and you have to solve for by integrating. So by integrating, everything boils down to this formula. So this formula comes from the theory behind this, and you can only use this formula when the Biot number is less than 1. Internally, it's very fast. Conduction is very fast as compared to external. If Biot number is less than 1. If it is greater than, the external is faster than. So it is a different case, which we have some tabulated or graph already are there to find out the. But anyways, so let's use this equation to find out the time. How much time required to solidify a molten metal in the casting? So are you ready? So let's do one problem. So let me show you over here. This is just a brief overview. I want to go over the slides for your convenience. This is the Fourier heat transfer. Have you taken the class heat transfer? Yes, that's good. You have taken it, so uh, you might understand it more appropriately. But this much, if you have not taken it, then this is sufficient to prove it. Conduction equals to convection. At least you know that mc delta t equals to a times heat over ah delta t times dt. Okay, now this is just the thermal diffusivity, and then this is for estimation. You see my point, guys? For estimation, time required to solidify or transfer is L square over alpha. And now let's go to the slide. uh, Biot number, Fourier and Biot in the 18th century. Yes. So let me cut and paste again. So Jean Baptiste Biot number, and this, have you understood this plate, that this is our we are not considering the infinite plate, which is in a semi-infinite plate, and the characteristic length is the middle of the thickness. If this is 2L, the middle is 1L, which is the characteristic length. You understood this point? So now you find when you apply this formula, you have to see. You will apply this formula when HL over K, where K is the thermal conductivity, H is the overall heat transfer coefficient, L is the characteristic length, V over A. So we will understand this. So we still have about some time. So let me go over one problem. So then we apply the equation for heat transfer. Final minus initial. And then you equate delta T. You see MC delta T, final minus initial. Here delta T means final. Where is that? Over here. Delta T, my final minus initial. So let me grab this formula just for your knowledge purpose. Okay. This is my going to be you see the same thing. Same equation comes. Conduction is happening inside the molten material, and convection is happening outside the air, outside the surround, like outside surface temperature. You see my point? Now, now from here you have to find out the formula. This formula comes out from this equation. You have to integrate it. And now let me show you the final step here. This is the form. Solving for time, you have to do some integration, and then I'm not going to derive it by integration, but I'm showing you that this formula should be in your formula sheet when you come for the test one. Let's use this formula in our question number 1. This is our question 1. You are interested in cooling. Please note down, gather information. Okay, start writing down in your notebook. Let's do the information here. So how much time you have to understand. Let me show you the next slide here. How much time required to cool down the plate? You are interested in cooling a zero point 0.5. The thickness is how much? 0. 0.5, so inches. So 2L. Thick plate of copper. Temperature, initial temperature is 500 Celsius. And the final temperature is how much? Final temperature is 50 Celsius. It is cooled such that the overall heat transfer coefficient, watts per meter square per Kelvin, and the sink temperature, surrounding temperature means sink temperature 20 Celsius. So let's find out. But before we do that, can you tell me what is the Biot number? Let's do this Biot number here. I'm gonna use this formula. This formula I'm gonna use for solving this problem. But for that, can we use this formula? You have to apply the Biot number verification. Let's do the verification of this formula. So Biot number says that HL over K. How much is H? 200. 200. L is L is how much? 0.5 divided by 2. What happens, sir? Is it 0.5 inch? 0.0035. What is our thermal conductivity? 93. Some data is missing. Thermal conductivity. Did I tell you that one? Let me see. 1 second. Yes. Some of the information is hidden here. The density is given, thermal conductivity is here. Yeah, so let's do this. But I think there is some unit conversion. So can you help me in meter? This is in inches because our K value is in watts per meter. So 393. It's a dimensionless quantity. Biot number is dimensionless quantity. So can you help me? Can you help me finding the answer in meters? What is this? L in this is in inches right now. Agreed? So let me write down L equals to 0.5 divided by 2 in inches. Can you convert it into meters? And then that value you will write down in meters over here. It's not in inches. This is the little catch, which is a trap for some engineers. So can you tell me, do you get this answer 0.00635? Because 1 meter is how many inches? 3.28 feet. Agreed? And 1 foot equals to 12 inches. So this is how much, like 3.128, 3.3.28 times 12. This is how many inches in 1 meter. And then 0.5 divided by 2 times 39.36. What happens, sir? Multiply? No. Yes, divide. Sorry, I multiple 4. So you see, is in you see it's in meters. So now when you do the math here, what value do you get? Yes, it is 0.00323, which is much less than 1. So it means we can apply this formula. You see, we have verified it. So before you apply, this is the check which you have to do in your casting time to solidify the casting. And let's do the math now. I'm going to use this formula here. Time equals to, I'm going to use this formula here. Time equals to, let's plug in the values here. Time equals to, let me tell you one thing. What is volume divided by area? This is the characteristic length. So can I write down L as point? What's that? 0.00323. Can you write down like volume divided by area, which is point? You don't have to remember the volume. You don't have to dig into the data to collect the volume, dig into to find out the surface area. Just find out the characteristic length. So you replace V over A as L. So I can write down 0.00323. I'm sorry, this is not the I missed. This is not the BO number. This is the characteristic length is 0.00635. So have you understood my point? The characteristic length is 0.00635. Agreed? So 0.00635. Density is how much? 8,970. That's the density of the material. 8,970. Specific heat is how much? 385 joules per kilogram per kilogram per kilogram per kilogram. 385 divided by the overall heat transfer coefficient. How much was that? 200. It's 200. Almost there. We open your calculators. I know time is running short, but you can still stay for 15 more minutes, right? You have a lot of time. 15 more minutes. Or let's finish this up, then you can go. Can you finish it quickly? How much do you get time to solidify this material? Open your calculator and then you can go. Yes, that's what I have. Ari Gamma, you are right. 304 seconds to solidify this time from that temperature, which is about 5 minutes. I'm releasing you 5 minutes early today. Okay.